Digital security is a structure built on math. We rely on the sheer complexity of specific puzzles to shield every private message, password, and financial transaction we send across the internet. To keep that data private, your device and a server use a pair of keys. The server shares its public key openly, allowing your computer to scramble your information into a code that only the server should be able to read. This relies on a one-way function. It is a mathematical process that is easy to perform in one direction, locking the data, but effectively impossible to reverse without the server's specific private key. A standard computer could eventually find that private key by guessing every possible number, but the math is designed so that the search would take millions of years. Our security is based on the hope that no computer can ever work fast enough to beat the clock. That calculation changes with the arrival of the general-purpose quantum computer. These machines process information using the principles of quantum mechanics, allowing them to navigate certain types of data much faster than any binary processor. Specific quantum algorithms can calculate the private key directly from the public one. By finding these mathematical shortcuts, a quantum computer can bypass the million-year waiting period and open the encrypted data instantly. If the math protecting the internet can be solved this easily, it is no longer a viable shield. To secure the future, we have to look past mathematical puzzles and toward the rules of the physical world. When math can no longer hide our secrets, we turn to quantum mechanics. By basing our security on the physical behavior of matter, we can create a lock that is defended by the laws of nature. A traditional bit is a 1 or 0, but a qubit exists in flux, representing multiple orientations simultaneously, like an arrow sweeping a circle. But you cannot watch it. Observation forces the qubit to choose a single orientation, permanently snapping it into a rigid state. You cannot copy the information to study it later. It is physically impossible to create a perfect duplicate of an unknown quantum state. If you try to read it, you change it. Try to copy it, and you fail. We have a unit of information that cannot be duplicated and effectively alters itself the moment it is seen. This is the foundation of a communication channel that detects its own intruders. In this scenario, you and a server want to create a shared secret key over a quantum channel. The server encodes a random string of zeros and ones into qubits, sending them down the line. When they arrive, you measure them with random filters. You both compare orientations, keeping matches and discarding the rest, leaving you with identical copies of a secret key. Now consider an eavesdropper trying to intercept that stream to steal the key for themselves. Since the spy cannot copy the qubits, they must measure them in transit. But without knowing the server's chosen orientations, they have to guess. When the spy guesses wrong, they irreversibly scramble the qubit. The trap is set. When you verify keys with the server, you will see the errors caused by the spy's measurements. The physical evidence of their presence is visible in the data itself. Quantum cryptography turns the fundamental laws of nature into a detector. It ensures that any attempt to listen to the conversation will leave a permanent, detectable mark on the message. Scaling this technology requires a massive overhaul of our digital infrastructure. To move qubits across the planet, we have to build dedicated quantum networks that can maintain these delicate states over long distances. Even then, quantum channels only secure the transmission. They don't stop a hacker from pretending to be the server you're talking to, or from simply flooding the network with noise to stop you from communicating at all. Quantum technology is a catalyst for transition. It renders the mathematical locks we use today obsolete, while providing the physical principles necessary to build a more resilient replacement. Beyond cryptography, these machines solve a more fundamental problem. Classical computers struggle to model the complex interactions of subatomic particles because they don't follow binary rules. Because qubits operate on those same quantum laws, they can simulate the behavior of atoms and molecules directly, mapping out new medicines and materials with high precision. The end of our current encryption standards is the price of admission for this technology. We are trading a system based on math for one based on the physical reality of the universe.